Sustainable Land Management. Regenerating Degraded Areas for Agriculture. Title: Sustainable Land Management. Regenerating Degraded Areas for Agriculture. Introduction. Sustainable land management practices are crucial for ensuring long-term food security and environmental preservation. This article will explore the importance of sustainable land management and highlight key strategies for regenerating degraded areas to create more sustainable and resilient agricultural systems. 1. Understanding land degradation. Land degradation refers to the loss of productivity and decline in the natural capacity of the land to support plant and animal life. It is often caused by human activities such as deforestation, overgrazing, improper irrigation, and industrialization. Areas affected by land degradation face reduced soil fertility, increased erosion, and decreased water retention capacity. Restoring these degraded areas is essential to reclaim and maximize their potential for agricultural productivity. 2. Benefits of sustainable land management. Implementing sustainable land management practices offers a range of benefits. Firstly, it improves soil health, enhancing its water holding and nutrient retention capacities. This, in turn, promotes healthier plant growth and higher crop yields. Secondly, it mitigates erosion, reducing soil runoff and sedimentation in rivers and lakes, thus preserving water quality and aquatic ecosystems. Thirdly, sustainable land management contributes to carbon sequestration, aiding in climate change mitigation by storing significant amounts of carbon dioxide in the soil. 3. Key strategies for regenerating degraded areas. A. Conservation agriculture. Conservation agriculture involves minimal soil disturbance, permanent soil cover, and diversified crop rotations. By adopting conservation agriculture techniques such as no-till farming, farmers can reduce soil erosion, enhance organic matter content, and improve soil structure. This practice also minimizes the use of synthetic pesticides and fertilizers, making it environmentally friendly. Bioagroforestry systems. Integrating trees with crops or livestock can enhance soil quality, reduce erosion, and provide additional sources of income for farmers. C. Terracing. Terracing is an effective technique used to control soil erosion on steep slopes. By constructing series of leveler gently sloping platforms along the contour lines, water runoff is slowed, allowing it to infiltrate the soil, reducing erosion and enhancing water retention. Terracing also provides additional flat areas for cultivation, increasing the amount of arable land available. Integrated water management. Water scarcity is a pressing challenge in many degraded areas. By maximizing water productivity, farmers can improve crop yields and resilience to drought. Soil restoration. Replenishing soil fertility is crucial for regenerating degraded areas. Implementing sustainable soil management practices like the application of organic matter, compost, biochar, conservation of soil biodiversity, and use of cover crops can help restore soil health. Additionally, promoting the use of locally adapted and drought-tolerant crop varieties can enhance plant resilience in degraded environments. 4. Policy and institutional support. Successful regeneration of degraded areas for agriculture requires supportive policies and institutions. Governments, international organizations, and NGOs must collaborate to provide technical assistance, capacity building, and financial incentives to farmers. Creating awareness about sustainable land management practices, offering training programs, and facilitating access to credit and markets will encourage farmers to adopt these practices. 5. Case studies and success stories. Numerous case studies and success stories demonstrate the effectiveness of sustainable land management practices in regenerating degraded areas for agriculture. One notable example is the Great Green Wall Initiative in Africa. This ambitious project aims to restore 100 million hectares of degraded land across the Sahel region by planting a barrier of trees. In China, the Grain for Green program has shown impressive results in combating land degradation. This large-scale initiative involved converting steep-slope farmland into forests or grasslands, effectively preventing soil erosion and restoring ecosystem functions. The program not only improved the livelihoods of rural communities by providing alternative sources of income, but also contributed to improved water quality and biodiversity conservation. In Brazil, the ABC Plan, low-carbon agriculture, has successfully promoted sustainable land management practices. The ABC Plan has shown that sustainable land management practices can be economically viable and contribute to greenhouse gas emissions reduction. These success stories highlight the importance of knowledge sharing and collaboration between different stakeholders. By learning from these experiences, policymakers, farmers, and communities can adapt and implement sustainable land management strategies that are suitable for their specific contexts. 6. Challenges and future directions. While sustainable land management offers tremendous potential for regenerating degraded areas, there are several challenges that need to be addressed. Limited access to financing and technical support often impedes the adoption of sustainable practices, particularly for small-scale farmers. Governments and development agencies must prioritize investments in sustainable land management programs, providing farmers with the necessary resources and knowledge to implement these practices. Additionally, changing attitudes and behavior among farmers and communities can be a significant hurdle. Traditional farming practices may be deeply ingrained, making it difficult to persuade farmers to adopt new and unfamiliar techniques. Furthermore, climate change poses additional threats to degraded areas. Rising temperatures, changing rainfall patterns, and increased frequency of extreme weather events can exacerbate soil degradation. Integrating climate-smart principles into sustainable land management practices will be essential for building resilience and ensuring the long-term success of soil regeneration efforts. 7. Innovative technologies. In addition to the strategies mentioned earlier, there are also several innovative technologies that can aid in regenerating degraded areas for agriculture. A. Precision agriculture. Precision agriculture involves the use of advanced technologies, such as GPS, remote sensing, and drones, to optimize agricultural practices. These technologies enable farmers to monitor soil moisture levels, nutrient deficiencies, and plant health in real time, allowing for targeted and precise application of resources. By utilizing precision agriculture, farmers can reduce input costs, minimize environmental impacts, and maximize crop yields. B. Biotechnology. Biotechnology offers promising solutions for regenerating degraded areas. Genetically modified, GM, crops that are drought-tolerant, pest-resistant, and nutrient-dense can help overcome the challenges posed by degraded soils. These crops have the potential to increase productivity and reduce the need for chemical inputs. However, it is important to ensure that adequate safety regulations and ethical considerations are in place when using biotechnology in agriculture. See hydroponics and vertical farming. Hydroponics and vertical farming are soil-less farming techniques that can be particularly useful in areas with severe soil degradation. Hydroponics involves growing plants in nutrient-rich water solutions, while vertical farming refers to the practice of cultivating crops in stacked layers, often indoors. These techniques conserve water, optimize space utilization, and minimize the impact of soil degradation on agricultural productivity. D. Remote sensing and GIS. Remote sensing and geographic information systems, GIS, enable the assessment and monitoring of land degradation over large areas. By analyzing satellite imagery and mapping data, decision-makers can identify areas that are most severely degraded and prioritize interventions accordingly. Remote sensing and GIS also facilitate the monitoring and evaluation of the effectiveness of land management strategies, enabling evidence-based decision-making. The biochar. Biochar is a type of charcoal produced from biomass. It can be used as a soil amendment to improve soil fertility and enhance carbon sequestration. Biochar has the ability to retain water, nutrients, and beneficial microorganisms in the soil, thereby promoting plant growth. It also acts as a long-term carbon sink, reducing greenhouse gas emissions. Incorporating biochar into degraded soils can significantly improve their quality and productivity. 8. Collaboration and knowledge sharing. Collaboration and knowledge sharing play a crucial role in advancing sustainable land management practices for regeneration of degraded areas. Governments, research institutions, NGOs, and farmers' organizations must collaborate to share experiences, best practices, and lessons learned. This collaboration can take the form of workshops, conferences, and networks that facilitate the exchange of information and expertise. Furthermore, engaging local communities and farmers in decision-making processes and knowledge sharing is vital for successful implementation. 9. Scaling up and replication. To overcome the challenge of limited resources, it is essential to scale up successful sustainable land management initiatives and replicate them in different regions. Identifying and documenting successful case studies, as well as providing technical assistance and capacity building, can support the replication of these practices. 10. Conclusion. Regeneration